In this video, we'll study the AC series motor and three-phase induction motor. Single phase compensated series motor, which is built for traction work, is of the order of several hundred horsepower, and they have low power factor at the start, due to which the starting torque is low. The AC series motor is not suited for suburban service because there are frequent stops, but it is extensively used or employed for mainline work on the continent and in America because it provides good service. The speed torque characteristic and speed current characteristic of AC series motor, it is similar to those of the DC series motor. If a DC series motor is worked on AC, then it will not operate in a satisfactory manner. The difference between DC and AC operation can be seen . So we have the DC operation, which is simple enough. I, which is the current drawn by the motor, IRSC is the drop in the series field, and IRA is the drop in the armature, and EB is the back EMF developed, which equals to K phi N. So the equation is V equal to EB plus IRSC plus IRA, which is nothing but K phi N plus IRSE plus IRA. Also, the drop IRSC plus IRA, it is about 10% of the applied voltage. Therefore, we can tell that EB, it is practically equal to V. On AC operation, the magnetizing component of the current and flux, they are in phase, and also the back EMF EB, it is in phase with the flux. So if the loss component is neglected, so loss component of the current, if it is neglected, we can assume the whole current to be in phase with flux. So the drops IRSC and IRA, they are in phase with current, while the drops due to reactance IXC, IXSC and IXA, they lead the current by 90 degree. So this is shown in the phasor diagram. So in this case, the back EMF, it is much less compared to the back EMF in DC operation. Also, the speed is proportional to back EMF, and torque, it depends upon the product of EB, back EMF and current. And since EB in DC operation is larger than in AC, for the same torque, the speed for DC operation it is higher than for AC operation. So we can see that in the speed torque curve for the DC and AC operation. So the speed versus torque curve is plotted for DC operation as well as AC operation. So since EB value is greater in DC operation and since N is proportional to EB and torque is depending upon the product of EB and I, and since EB is greater in DC operation than in AC operation for the same torque, speed for the DC operation it is higher than that of the AC operation speed. So in order to improve the performance of the motor on AC, a compensating winding will be connected in series with the armature, or it is short circuited on itself. So the effect of this compensating winding is to reduce the armature reactance of the motor, which will increase the EB value, and hence it will provide better speed regulation. The armature and the field MMF, they will be at right angle to each other, and this compensating winding it will provide a MMF which is opposite to the armature MFF, and therefore it will reduce the armature reactance drop. So we can see the circuit diagram and phasor diagram of the AC series motor with compensating winding. So the AC series motor is connected in series with the compensating winding. To reduce the armature reactance drop. So this is the circuit diagram of the AC series motor when connected with the compensating winding in series with it to reduce the armature reactance drop. And the phasor diagram for this circuit we see in the next slide. So in the phasor diagram we have current in phase with the flux phi, and the drop in the series field winding IRSC is also in phase with flux phi, and the drop in the series field winding due to reactance is 90° out of phase with flux phi, that is it is leading flux phi by 90°, that is IXSC. And then we have the armature and compensating winding drop, that is IRA plus RC, which is in phase with flux phi, and the drop due to the reactance of armature and compensating winding IRA plus XC is 90° leading the flux phi, and the back EMF voltage is also in phase with the flux phi. So the RA plus RC, it is the resistance of the armature and compensating winding, and XA plus XC, it is the reactance of the armature and compensating winding. Next we'll see the AC series motor having a compensating winding which is short circuited on itself. So this looks like a short circuited secondary of a transformer, and it will greatly reduce the effect of the armature reactance. So in the phasor diagram we can see the term RA dash and XA dash, which is the equivalent resistance and reactance of the armature and compensating winding, which is referred to the armature circuit. So the use of compensating winding will improve the power factor of the motor, so which can be seen in the phasor diagram. Next is three-phase induction motor. Though the construction of three-phase induction motor is simple and it is robust, there are few drawbacks of three-phase induction motor. That is, there is difficulty in starting of the motor, as well as speed control of the motor doesn't make it suitable for traction work. Also, the speed torque curve of the induction motor is flat, but it has been used in the condo system in Hungary country, as well as some parts of Italian state railways.